the previous videos, we mentioned about the detailings of the structural element. This detailing will refer to the structural key plan as well as the details given for each structural element. We mentioned about the issue with the line type and the line width, which different types of the line give you different informations. We also mentioned about you need to differentiate certain line width, especially when you have the same line type to carry different informations. This will be reflected after the printing in order to avoid ambiguity and confusions to the person who reads your technical drawing. We also mentioned about the issues of printing, where there are many things that you need to consider to prevent the printing problem leads to ambiguity or problem that hinder the effective delivery of the informations between parties. All these need to be careful. Now in these videos, we're going to proceed with our discussions with some detailings of the structural element, and probably we also demonstrate some of the members for you to have an idea how you can do the detailings for the members. First, let us look at the beam. These are the informations and the considerations that you have to consider when you do the detailings for the beam. First, you need to clearly indicate the name of the beam, and this name of the beam, it will be on basis of your structural key plan. It must be in line so that the contractors is able to locate which beam it is referring to in your structural key plan. Your detailing also give an idea what type of beam it is. Is it a continuous beam? Is it a single span beam? Is it a cantilever beam? This can be seen from the appearance of the columns supporting the beam, and the column needs to be consistent with the informations given in the structural key plan in terms of the width, in terms of the locations, in terms of the distance from the grid line, and also in terms of whether it's penetrate above the beam or stop at the beam top level. These need to be clearly indicated. There will also be the reinforcement bar indicated within the detailings. There will be shear links. For deep beam exceeding 750 mm, there will be longitudinal surface rebar that are used to control cracking on the surface of the beam. There will also be the lapping, indicating the locations of the lapping as well as the required lapping length. Also, in the detailings of the beam, the cross sections of the beam will also be indicated. Demonstrate that the existence of the slab adjacent to the beam. Is it going to be single beam only without any slab, such as roof beam, or is it going to be slab attached to the beam, some at both sides, some at one side, or some at the topping height? These need to be clearly indicated. There will also be the grid lines come together with the dimensions, and this line needs to be in line with the structural key plan. It is for you to be able to locate the members as well as to know the elements within certain stretch of the members. Keep the contractor notified all the necessary details within the members. There will also be labels for the details appear in the members, such as the reinforcement bar, how many units, what are the size of the reinforcement bar, what kind of reinforcement bar it is it Y bar or is it R bar. There will also be levels for the shear link, the size of the shear link, and the spacing between the shear links, and so on and so forth. You need to be careful with the adjacent slab, whether there are one slab adjacent to the beam or two slabs adjacent to the beam, or the beam itself is alone without being attached to the slab. And this will be reflected in the detailings. where there will be solid line in front of the beam to indicate you can see the edge of the slab, which in this case it will be top and soffit of the slab. And there will be hidden line to represent that the slab is actually behind the beam. The hidden line will represent the top and the soffit of the slab behind the beam. Be careful with the incoming beams. You need to correctly indicate the size of the incoming beams. It is so that you can imagine the relationship between the beams at their joint to know which one it will likely to be the primary beam and which one is more likely to be the secondary beam. It also gives you informations to see the incoming beams attached to your beam member, giving you an idea in terms of the structural integrity between the joints. There will also be columns, which we mentioned just now. The dimensions need to be correct. Whether there are columns penetrating above the beam needs to be clearly indicated, and sometimes the existence of the stiffener need to be clearly indicated as well. That you need to show the locations of the stiffener, that we know there will be a point load acting onto the beam. And some engineers also provide indications the locations of the staircase. How does the staircase are connected to the beam? Next, remember the cantilever beam. They act differently than the continuous and simply supported beam. The cantilever beam will have the compressions at the bottom of the beam and tensions at the top of the beam, which is the reverse way as compared to the typical beams. In that case, the main reinforcement bar, it will be on top of the cantilever beam. And when you come to the cantilever beam, you will need to be careful, as typically engineer will do it more conservative to avoid failure due to the cantilever. Also, when you provide the reinforcement bar, remember that you need to provide the main reinforcement bar at top of the support, as typically you are dealing with the continuous member. There will be moment at the midspan and at the support. At the midspan, tension will be at the bottom of the beam, and the compressions, it will be on top of the beam. However, at the support, it will behave in the opposite manner, where the tension now, it will be on top of the beam, and the compressions, it will be at the bottom of the beam. Therefore, when you provide the main reinforcement, especially at the support, you need to make sure the main reinforcement is on top of the beam. Next, you need to be careful with the minimum 20% of the hanger bar. This one, you might not be able to understand this. Let me show you this diagram. Let's say now you have a continuous beam here, where there are extensions from here and extension from the other side. This is just one stretch of the continuous member, and you know that at the support you will need to provide tension reinforcement bar at the top of the beam because of the negative moment. This also happens at another support of the continuous member, which you will need to design an adequate length here for the top main reinforcement bar to stop within the members, so that it is able to take this negative moment. Same goes to the other support here. Now what happened here is, you will know that these regions might not be subjected to high degree of the tension force, and it is likely to undergo the compressions only. As the midspan, the tensions, it will be at the bottom of the beam, and compressions, it will be on top of the beam. That means there will be a significant change in terms of the stress in the concrete from the tensions to neutral, and then to the compressions, and then to neutral, and then to the tensions. Now you need to provide reinforcement bar to take the stress, both in tension and compressions. You know that the concrete is weak in tension. That's why you need to provide a lot of reinforcement bar at the support. However, the concrete is really good in compression. Most likely concrete itself, if you provide adequate size of the beam, it is already sufficient for you to withstand the compression stress. Now that you only require the minimum reinforcement bar as a compression bar, which based on the industrial practices, the smaller size that you're going to use, it will be T12, and you require a minimum of 2 units, one at each corner of the beam. Ultimately, you will have this hanger bar to be 2 T12. Now back to the problem that we mentioned just now about that 20% hanger bar. What happened here is you have the reinforcement bar quite heavily reinforced at the support, and at the midspan here on top of the beam, the amount of reinforcement bar is not much, only 2 T12. And if you do comparison between the highest amount of reinforcement bar as compared to the amount of reinforcement bar as the hanger bar here, the areas of the reinforcement bar here is less than 20% of the areas here. This will lead to a situation that the support is quite heavily reinforced, while the midspan will appear to be relatively weak. This will lead to a situation in case of the distributions of the stress, especially when the members is reaching to its capacity, there will be concentrations of the stress at the weakest portions of the members. You do not like this to happen. You do not like the hanger bar is unable to effectively disperse the stress to the nearby elements of the member, which in this case, you need to increase the amount of the reinforcement bar slightly to ensure it is more than 20% out of the large amount of reinforcement bar at the adjacent support. This is the idea of 20% hanger bars. We have not covered this in any part of the reinforced concrete design, which I did not see in any part of the reference mentioned about this. The one I mentioned just now is purely my personal interpretations and assumptions. But how can this 20% hanger bars concept come about? It is notified by the software. Software will notify you when you do the modeling that you have a situations where your hanger bar is less than 20%, which the software will recommend you to increase the bar size so that it is more than 20%. The table here gives you an idea how you can convert those. This one is for quick reference. In fact, you can develop your own table here, or you can actually do some basic calculations. What you can do here is, whenever you encounter the support, go for the support with the larger amount of reinforcement bar, and then check against the amount of reinforcement bar as the hanger bar. See if it is less than 20%. If it is less than 20%, maybe you just increase the bar size or slightly increase the amount of reinforcement bar in order to pass the minimum requirement of 20%. The list here, it gives you something like this. Let's say now at the support here is 3T25, which give you a total area of this. You will require at least 2T16, which you cannot use 2T12, in order to ensure you have at least 20% of the bar area. Let's say now you have the support to be more heavily reinforced, for example 4T25, and then you require 2T16 for the hanger bar, and so on and so forth. Since that we are introducing this slide, we mentioned in our previous videos a good aspect ratio for the beam section, it would be 0.3 to 0.6. In order to fulfill this ratio, this table is developed with the beam width and with the applicable range between the minimum and the maximum height. Let's say now you're talking about the beam width of 150, The common size that we normally use, it will be 150 times 300 or 150 times 450, which is actually within this range of 250 to 500. In fact, you can use this, only that it is not that common in the industry. But technical wise, it is viable and it is quite optimized. In the case that you require larger beam size, then you may have deeper beams. Now that we have covered the theoretical part about the detailings of the beam, maybe let us look into some examples. Let's take a look on this beam. This is a typical detailing of a beam. You will see grid line here. This grid line will need to be in line with the structural key plan, and there will be naming for the beams. That means you are talking about C2, 7A to 8B. That means this beam here is actually on the grid line of C2, and it ranges between 7A to 8B. And this grid line, the dimensions needs to be checked against the structural key plan. This is the beam that you are talking about, and there are incoming beams. And you need to be careful, this incoming beam need to also be in line with your structural key plan in terms of its positions, whether it is on the edge, or whether it is at the center, or whether it is at the offset distance. And then you need to indicate the reinforcement bar. Don't forget the naming need to indicate the size of the member, which in this case is 150 times 300. Then you indicate the reinforcement bar 2T12, as well as you need to indicate the shear links. Normally the shear links are indicated in the mode of the type of the bar, as well as the size R6. The spacing, it will be 175 here, and within this range here, you will estimate they will require 9 units of the shear link. There will be a cut section here, which is indicated with the number of 75. If you look at the cut section 75 here, your beam size is 150 times 300. You will expect there are 2 slab adjacent to the beam, one with a certain dropping height from the top of the beam. And you have the second cut section here, 75A, which if you look at the cut section here, there will be slab on one side only. The cut sections give you the dimensions and the existence of the slab adjacent to the member. It also gives you information regarding the amount of reinforcement bar, how the reinforcement bar are being placed in the section, as well as the shear link. Next, we talk about the top reinforcement bar at the support. You need to indicate where the top reinforcement bar should stop, normally in reference to the grid line, which in this case is 750 from the grid line 7B, and you need to indicate the lapping length between 2 reinforcement bar, which in this case you are talking about 2T20 for the bar here and 2T12 for the bar on this side. That means there will be lapping length between the 2T20 and 2T12. Also, you need to take care of the lapping length for the bottom reinforcement bar, which in this case you have 2 different sizes of the reinforcement bar. Again, you need to calculate the lap length and to be indicated. As for the lapping of the reinforcement bar, normally we do it at near the support, because it is beneficial at the regions of high shear, and the tension resistance of the reinforcement bar may be questionable at the high moment region. To avoid that, normally we'll put the lapping near to the support and not at the midspan of the member. Maybe we look at another example here. This is an example where you have beam of different sizes. There will be incoming beams, and this is a continuous beam. However, there is a 50 mm drop, and the size of the beam here is slightly smaller than this one. That means you need to be careful with the reinforcement bar, how it is being properly laid. Indicate the reinforcement bar required, indicate the shear length required, as well as the numbers of shear length, indicate the cut section, and also indicate the top main reinforcement bar at the support, as well as the required lapping when the bar size is different. And because of the drop of the member and because of the smaller size of the beam, there will be reinforcement bar embedded inside the member. You know that the reinforcement bar performs the best when it is in the straight line. Therefore, it will be good for you if you have sufficient embedded length. Then you can put the reinforcement bar in straight line. Indicate the exact locations where you can have the reinforcement bar being cut. Next, let us try another example here. This is a deep beam here. The level of the beam given. The section size is 230 × 600. It stretched from 4A to 5C, which is reflected from the grid line here, 4A until to 5C. Clearly indicate the incoming beam as well as the respective slab. The slab here, solid line, means that you're going to see the edge, and indicate the amount of reinforcement bar, and indicate the columns. There are columns not extended to the upper side of the beam, and there are columns actually penetrating through the beam. And this column here will need to be in accordance to the size of the columns as given in the key plan. Indicate the amount of reinforcement bar required. Do some curtailment. Indicate the locations where you can reduce the amount of reinforcement bar near to the support. You see here there is an offset distance between the grid line and the starting of the beam. It would be good if you indicate the distance clearly so that the contractor have some ideas without requiring to refer to the structural key plan. There will be cut sections, which based on the section 99, it should look something like this. Theoretically, you should have every single stretch of the members to have cut sections, but this is going to make the drawing to be rather messy. Based on what information is given in the cut section here, the arrangement of the reinforcement bars are identical. You have 3 rebar at the bottom, 3 rebar at the bottom, 2 rebar on the top, 2 rebar on the top, and you have 2 surface bar here as indicated here. That means 2T12. The 1 times 2T12 means there will only 1 longitudinal bar required. If you have a 2 here, that means you will see 1 and 2 longitudinal bar. And the 2T12 here, it means that the 2T12 here, that means you have 1 and 2 T12. The dimensions are clearly indicated. Do some necessary curtailment where you have 3 T25 at the midspan. Now you have only 2 T25 near to the support. Clearly indicate where you can cut that additional T25. As for the intermediate support here, you will expect the main reinforcement bar here at the top of the beam, and you will need to indicate this main reinforcement bar have to reach where so that the supports are resist with good stability. This one, it will be dependent on the bending moment diagram, especially at the support, which in this case a lot of reinforcement bars are required and indicate where it should stop. And because of the size of the rebars are different, there will be lapping between the reinforcement bars, indicate the lapping length. And you see a large amount of reinforcement. Most likely you need to check if this one fulfill that 20%. You can go back to the table here, which the reinforcement bar at the support is 3T25 plus 2T12. That means the smaller size of the reinforcement bar, it will be 2T16. With that, this is more or less about the detailings of the beams. Having this to be demonstrated, maybe you can apply the principles and have some guides for you to produce your own detailings of the beams.